Okay, today we're going to talk about sorting. We're going to spend just a little bit of time today laying the groundwork for what will become multiple lectures on sorting. Now, sorting in a class on data structures, sorting is not a data structure, but it is central to many of the tasks that we have to perform, and it's a excellent chance for us to practice our analysis skills. And there are also many approaches. So it's good to know many of these approaches because they will come up over and over again in other contexts. So, what is sorting good for? Well, it's good for giving order to information. Primarily, we would like to sort things so that we can find them quickly later when we have to search for them. What kinds of things might we want to sort? Well, things like an ancient reference is the phone book. The phone book is this very thick book which stores a list of everyone who belongs in the phone book who owns a home phone or businesses, and we want to keep them in sorted order because we want to be able to find them quickly. Imagine, I like to give the example that what if every city just appended each new person that came to the city to the phone book? Then, if you wanted to look someone up, you might have to look through everyone who has ever lived that is in the phone book because there's no order to it. Whenever you're using the web search to search for things, if you're using Google or some similar search engine, uh, Google might find for you 10 million or a billion hits that are relevant to your query, but you don't want to have to go through all of them. So it very helpfully sorts the most relevant ones to the top of your search results, so that you hopefully can find it on the first page or within the first few hits, um, saving you a lot of work on searching through that list of hits. When you're shopping, you might sort things by price. Um, an interesting application is, suppose that you had a whole bunch of uh, say integers or any kind of object that you might be interested in storing, and you have possibly a lot of duplicates in your array or your list of things. If you sort them first, then finding those duplicates is very easy because all of the duplicates will be next to each other. So after you've sorted the data, you can find the duplicates just by looking at each pair of items that are adjacent to each other and seeing if they're the same. I also always like to bring up the topic of books in the library. Books in the library, of course, are sorted by the Dewey Decimal System. And this is the point at which I would usually, in my class, if I were with you, show you the video Conan the Librarian from the movie UHF. Look it up. I will warn you that there is cartoon violence in the clip, but I encourage you to look that up. Weird Al as playing Arnold Schwarzenegger as a librarian. It's great humor. So the main things I want to talk about today, besides this motivation, is talking about the foundation, the framework, the lens through which we'll look at the problem of sorting. So we're going to look first at some of these questions, and we'll address these on and off as we talk about the algorithms. We're going to talk about what is the running time for each sorting algorithm in the best and in the worst case. So when we say best case, we mean how quickly could this algorithm sort the data if the data were, say already sorted or nearly sorted? And in the worst case, what if the data were jumbled up massively? What's the longest it might take? And can we sort faster if we have some limitations or some restrictions on the type of data that we have, say small integers, for example, as opposed to just any integers? Can we sort without using extra memory? This is sometimes called sorting in place. Can we sort without having to copy the data to another array and then copy it back at any point? And of course, this is possible. We'll see various algorithms that do this, but for some algorithms, it's not as easy. Um, we'll talk much later about what if the data that we want to sort is too large to fit in memory all at once? Well, of course, we could store it on disk, but how do we do that efficiently? And another question that we'll talk about is a sorting algorithm stable? And when we say stable, a stable sorting algorithm is one which does not reorder items if they are equal. So for example, if I had an array that looks like this, 9, 3, 5, 3, 2, okay? And I were to sort that, it would become 2, 3, 3, 5, 9. But the question is this 3 and this 3, are they the same? Or did the 3's get swapped? Okay, so is this the first 3? Or is this the first 3 in the original list? A sorting algorithm is stable if the first occurrence of an equal item is still first in the resulting sorted list. In other words, if two things are equal, they are kept in in the same relative order. Some algorithms are naturally stable, some are not. Okay, finally, a list of 6 assumptions that we're going to make as we talk about sorting. Very basic assumptions, but we'll refer to them from time to time, so it's good to write them down or to talk about them. First is that we're going to be sorting arrays of integers. And usually we'll assume that those integers are unique, but not always. Secondly, the length of the array is n. Thirdly, we're sorting from least to greatest. Fourth, we can access any element in that array in constant time because it's an array. Fifth, and this is requires a bit more explanation, we're going to compare items in the array using only the operator less than. So we're not going to use equal equals, we're not going to use greater than, we're not going to use less than or equal to. And if you've been in my class for some time, you know that we try to use as few operators as possible, and this is to impose as few restrictions as possible on the people using our code. Because if it requires less than, then we can only require less than of the people using our code. But if we also use greater than, then the people using our code have to provide a greater than operator as well. Okay, so, and this is also what we call, this is going to be a comparison-based sort, okay? So when we compare only using less than, what we're talking about, we commonly call this a comparison-based sort. And finally, our last assumption is that when we do our analysis, typically our analysis counts everything that happens, but for sorting, we're going to pay special attention only to the number of comparisons. In other words, the number of times that we call the less than operator. Okay, so those are our basic assumptions. That's the groundwork. And next time we'll dive into some details on sorting algorithms themselves.